Thank you very much, Clive, and thanks very much, everyone, for coming out on this rather warm evening, which is really impressive for someone even from Australia. So, synthetic intelligence. So what is intelligence? It's something that is quite subtle and very difficult to put your finger on. The adjective synthetic refers to something that is man-made, that is a replica of something that occurs in nature. So we often use the word synthetic when we're talking about synthetic fabrics, for example, or perhaps synthetic molecules, like insulin, for example. So synthetic intelligence kind of gives the connotation that it's intelligence that we're making ourselves. But how does it differ from artificial intelligence? You're all probably quite familiar with artificial intelligence, even though you might not fully understand it yourselves. So my talk this evening is actually going to be about this new thing called synthetic intelligence that is actually quite different from artificial intelligence. And I'm going to tell you a little bit about how it differs and why it's important, and how it might bring us even closer to understanding real human intelligence. I've kind of divided my talk very roughly into three parts. The first part of my talk, I wanted to put things into context and just give you a really broad overview of what artificial intelligence is. And I'm going to do that because I want to explain to you why artificial intelligence is artificial, how it differs from real human intelligence. And then I'm going to tell you a little bit about some cutting-edge research that involves actually making man-made devices that replicate the human brain, a synthetic brain, and how we can try and emulate thinking processes from these devices that we've made. In the last part of my talk, which is going to be the shortest part, I'm just going to kind of wrap up a little bit with some ideas, some viewpoints of my own. And of course, I'll be looking forward to hearing your comments and questions afterwards. Before that, as Clive mentioned, he's also going to have a bit of a discussion with me around this topic as well. So let's get started. So all of you by now have heard of artificial intelligence. In fact, the world seems to be infatuated with artificial intelligence. It's been applied to everything from social media to constructing IKEA furniture. But as I indicated, artificial intelligence is artificial. But why is it so successful? How does it work to make it so successful? Well, all it is, it's something that takes some data, puts it into an algorithm, and the output of that is predictions. Now, an algorithm is nothing but some mathematics and some code, and there are different types of programming languages that you can use to code up the mathematics. The mathematics basically just describes different ways to analyse the data. And the different ways of analysing the data depends on the different types of data that you're interested in. It might be social media data, or it might be some other kind of recognition data, like if you want to recognise car number plates, for example. Now, the outputs of this combination of data and algorithms is predictions. Importantly, these are statistical predictions. So that means that they have some inherent uncertainties that depend on the amount of data that's available to be processed and analysed. The reason why artificial intelligence is called artificial intelligence is because prediction itself is something that the human brain does really, really well. It's actually a hallmark of intelligence. And so hence the adjective here of artificial intelligence. The artificial comes in also because essentially what this is doing is just brute force analysing lots and lots of data. But in addition to the quantity of data that's required for artificial intelligence, it's also the quality of the data that matters. If you have insufficient amounts of data or poor quality data, then the predictions that that AI machine makes becomes less reliable. So, for example, if you have a whole bunch of data where, for example, you do want to recognise patterns on licence plate numbers, for example, if you throw in some random data into the mix, your predictions will actually then result in larger and larger uncertainties, becoming less reliable. So both quality and quantity of the data are hugely important in artificial intelligence. Now, the algorithm in artificial intelligence is also important, and probably the most exciting types of algorithms that are now used in AI are algorithms referred to as neural networks. And they're called neural networks because they do, in some ways, resemble the human brain, at least in the way it operates. So they're loosely based on the human brain in the following way. The algorithms use something called networks to connect different bits of information together. And they also iterate through the data at varying degrees of levels. And these varying degrees of levels also means that sometimes these algorithms, neural networks, are also referred to as deep learning, the deep indicating how many levels of iterations you go through to analyse the data. Now, neural network AI algorithms are most commonly used for pattern recognition. And again, this rings back to the intelligence part of artificial intelligence, because the human brain is actually really, really good at recognising patterns. You think about, when you're out on the streets of London, for example, out of all those people, if a friend of yours was on the other side of the street, you'd be able to recognise them instantly. So the brain does this remarkably well, and these neural network algorithms do this remarkably well as well, provided that there's good quality data and a large quantity of it. And of course, we're in the 21st century, we have the internet, so we actually now do have really large quantities of data available at our fingertips, and the quality is actually very, very good as well. And this is the reason why neural network algorithms were first invented in the 1970s, but are only now enjoying this renaissance because we have so much data available to us. Now, probably the most famous example of the application of neural network algorithms in AI was IBM's DeepMind AI, which beat the chess grandmaster Garry Kasparov in 1997. And Garry Kasparov has actually written a book recently about this, and he's actually a very strong proponent of AI himself, despite the fact that he was beaten by a machine. Another popular example is Google's DeepMind AI, which was designed specifically for playing the Chinese game AlphaGo. And a very recent development in AlphaGo was AlphaGo Zero, which is a further development on the original AI algorithm developed by Google that now doesn't need to play against any other human being. AlphaGo Zero actually taught itself by playing against itself to optimise how it plays this particular game. So things are developing at a pretty rapid pace, and it's very impressive. However, both those two examples, playing chess and playing AlphaGo, represent the fact that those applications of AI demonstrate that AI is really still very limited to specific tasks. And so there's a big push on at the moment for developing and extending AI further to try and realise artificial general intelligence. So in other words, how can we get these AIs to actually be successful at broader ranges of data, not just data that is relevant to chess or relevant to playing AlphaGo, but relevant for broader applications. This is really important because the way the human brain works is through general intelligence. We have the ability to triage and filter very broad bandwidth data and information that we are constantly taking in all the time, as you are all doing right now. We're doing this on the fly, in real time, with minimal effort. Our brains are doing this over and over again. We don't need some other entity to input data into us, to pre-program us, and we can actually do a broad range of general tasks. So whether AI, as it exists at the moment, can actually achieve that is really a major research direction for many research groups, but also for some of these major tech companies like IBM, which just last month actually demonstrated an example of moving towards artificial general intelligence with their Project Debater, particular AI. Now, the Project Debater AI, developed by IBM, was actually designed so that it could engage in debate with human beings. It was incredibly impressive because it really started to get closer to reason. You know, it was presented with two topics, and it was engaging with two human beings. And it was required to present a viewpoint, present a rebuttal, and also to do a wrap-up in a standard debate format. However, it's not true general artificial intelligence because it still needed to be pre-programmed. It needed to know what those two topics were. Data needed to be input into the system related to those two topics, and the right algorithms needed to be put into place in order to be able to achieve that. So there's still a way to go towards that. So what I'm actually presenting tonight is the question, is there a different approach to general intelligence, emulating into general intelligence? An approach that's different from the software-based AI approach. So that's what I'm putting to you this evening. Now, of course, we have actually seen some examples of what I'm referring to as a synthetic intelligence approach to understanding and emulating general intelligence through movies such as Ex Machina, for example, and the TV series Humans, which I gather is popular here in the UK. These examples are, of course, fictional, and we've got a long way to go to try and getting close to this, but they do present some interesting ideas that perhaps are not too far away from the distant future in terms of realising synthetic intelligence. And they really do show that the most important aspect of the human brain and how it thinks and how it demonstrates intelligence is by being interactive with its environment. As I mentioned before, gathering information, being exposed to information, processing that information in real time. And most importantly, the human brain and human intelligence is resilient against random things happening. And this is probably the most important limitation of AI software-based approaches to general intelligence. The fact that they're so reliant on curated data and large quantities of data, whereas the human brain and human intelligence that results from processes that are happening in the human brain can actually deal with random things being thrown at it. We deal with that remarkably well. So our brains actually have this enormous capacity to be adaptive and resilient against any types of data. So that's the challenge that we really face with trying to emulate general intelligence. And this is why it's actually valuable and important that we come up with alternate approaches to the software-based AI approach. So I'm asking the question this evening, can we make a physical brain-like device with intelligence? So in other words, I'm asking the question, can we view intelligence as a physical phenomenon. So in other words, something that can be described in terms of physical processes. If we can describe it in terms of physical processes, then we can actually build a device that replicates those physical processes. In other words, we can actually build a synthetic brain that's a replica of the human brain. So, importantly, this is not just about making a robot. So robots as we know them today are actually still controlled by software, computational software. They need to be pre-programmed. So what I'm talking about is taking, a machine or a device or something and putting inside it a synthetic brain so that it can then engage and interact with its environment and learn in the same way that human brains learn. So how do we do this? What are the first steps? Well, the human brain is made up of brain cells, which are called neurons. But these neurons are also compartmentalised into different regions of the brain. And these different regions of the brain also have different functionalities. Now, importantly, the individual neurons are connected together. And the different compartments of the brain are also connected together. So the whole brain is kind of like this really complex network, and there are different levels of the network that is the brain. So this is where we need to start. Two aspects. One is we need to be able to understand how the brain functions at the individual neuron level and how those individual neurons are connected together. And also then how they form these compartments which are also connected together. And the second thing is, moving away from individual neurons themselves, we also then need to understand what happens on the global scale. And this is quite interesting because at the individual neuron scale, what happens is that neurons come together and they communicate together. And we know that's an important aspect of how the brain works. But when we take the brain globally and we consider the really complex networks that form between neurons and between different regions of the brain, there's something else interesting that happens. Those interactions between neurons and between different parts of the brain actually result in emergent properties. And that's really important. What that means is that the whole is greater than the sum of its parts. And we see a lot of this type of behaviour in other complex systems. So in the brain, it's really important to be able to try and replicate the complexity of the network that exists in the brain in any kind of synthetic brain that we are attempting to recreate. Now, going back to the individual neuron level, what happens with the neurons in the brain is that they're all connected to each other. And when they get stimulated by electrical stimuli, they start sending signals to each other. And the signals that get transmitted through the neurons, which are connected with each other, is the way in which signal transmission occurs through the brain. So it's communication between neurons. So what I'm going to show you now is a YouTube video that demonstrates synapses. Synapses basically are the way in which individual neurons communicate with each other. And could you play that movie for me, please? Thank you. So this YouTube video shows how sensory input into the brain that comes visually or through smelling things or touching things and so on, results in electrical signals in the brain. And these electrical signals then propagate through the neurons, and the neurons kind of have these branches that stretch out and touch each other, or almost touch each other. So you can see that kind of tree-like branching structure between the neurons. And those tree-like structures, branching structures, are important because at the end of them, you can see that one end of one of the neurons almost touches another neuron. And the gap that forms between those two neurons, you can see tiny little molecules which are called neurotransmitter molecules, and they actually travel from one neuron to another. So those neurotransmitter molecules represent the way in which signals get transmitted through neurons. Now, the brain has approximately 100 billion neurons in it, but it has 1,000 trillion synapses, and that's because each of those neurons can have multiple synaptic connections with other neurons. So the first step in trying to design and build a synthetic brain is actually to try and start with the neurons and the synaptic connections between the neurons. Can we actually start with that and build those first? Well, of course, the answer is yes. And there's already a lot of research being done on that right now. And I just saw the slide that I wanted, that one, thank you. So the first step is, can we build synthetic synapses? These are the ways in which two neurons can communicate with each other. And in the real neuron case, they communicate with each other through these neurotransmitter molecules. So can we build a device that replicates these synapses? So there's a lot of research being done in this around the world, and with some really remarkable and impressive results. A lot of the efforts in this are focusing on using semiconductor electronic device components. And the reason for this is, if you remember, I mentioned that the human brain, once it receives sensory input, that actually sends out electrical signals through the human brain. And those electrical signals are what drives those neurotransmitter molecules from one neuron to the other. So since this process is driven by electrical signals, then it makes sense to start emulating this with electronic devices. So that's what a lot of groups have done. They've started with known electronic devices and trying to construct these kind of synthetic synapses and then setting electrical signals through them and seeing if they can kind of get something that looks like the way that real synapses work. So there has been some remarkable success in this, but there are two major drawbacks. So one of them is that once you start using electrical device components, and these are just things like stuff that you make integrated circuits out of, you know, there's nothing new here. But once you start using them, you're immediately restricted to working on a 2D, two-dimensional integrated circuit board, which is nothing like what the brain is. The brain is a 3D structure, right? But also, it turns out that electrical device components on a circuit board, you can't really manipulate them too much. First of all, they have to be very sparsely and carefully arranged. And that is completely unlike what happens in the real brain. So I've mentioned to you already that the real brain has some 1,000 trillion synapses. So these are incredibly dense connections, and we just cannot replicate that with existing electronic device components. The second problem with this approach is that electronic device components, as they exist today, actually use quite a lot of power. So we're talking about megawatts of power, whereas the human brain uses milliwatts. So that's 1 billion times more power that's used by these electronic device components. That's a real problem. However, that problem is starting to be solved through an approach known as neuromorphic computing. So the term neuromorphic means brain-like, and IBM has actually developed a new type of chip technology called neuromorphic chips that has now reduced the power consumption of their chips down to levels that are comparable with the brain. That's been a remarkable achievement. Their main objective in doing this was really to try and reduce the power consumption in computing and computing processes, particularly for AI applications. The power consumption is a real problem, and it's something that I'll come back to later on as well. So they've been quite successful in this, but they're neuromorphic chip devices which work because they've actually been able to completely scrap with the original so-called von Neumann type architectures of computer chips that were developed in the 1950s that we still use today. So they completely scrapped that and completely changed the architecture of their chips to achieve those really low power consumption levels. But the thing is, their chips are not synaptic-like, so they're not synthetic synapses. So this still doesn't sort of get us anywhere closer to how we can start building a synthetic brain. But there is another technology which is called the atomic switch technology. And it was only relatively recently commercialised by the electronics company NEC, it's a Japanese electronics company. And this is a completely new technology. It's not based on semiconductors. They've really started from scratch with this. And it's called atomic switch because it acts like a switch going from an off state to an on state. It's able to make that transition extremely rapidly in milliseconds, if not shorter timescales. So it's already quite attractive for computing applications where you're working with binary zeros and ones. But it's also called brain-like atomic switch because it turns out that the way that these switches operate is exactly the same as a synapse. You have two regions with a gap in between, and when you put an electrical signal across that, you drive ions from one side to the other. And that is exactly the same as the way in which neurotransmitters transmit electrical signals in neural synapses. So this has been a really exciting development. And there are other really attractive features of this atomic switch technology, such as they have very low volatility, which means they don't need to be maintained as often as existing semiconductor device technologies. And they have extremely low power consumption as well, again, similar to what the brain uses as well. And in fact, NEC's first application is to put these devices on space satellites because then they don't have to worry about them. There's low maintenance, low volatility, low power consumption. So this is really an exciting new technology, and it's a technology, as I said, that mimics the way that synapses work in the human brain. However, as you'll see with this particular device, it still faces a limitation in moving it to the next stage of building a synthetic brain because it turns out that the individual synapses are still quite limited in terms of the way they can be arranged and how many connections can actually be achieved out of them. So at the moment, it's very difficult to achieve a high density of connectedness with these atomic switches. That's something that people are working on, but at the moment, we're not there yet. Now, this is a schematic illustration of what a real network of neurons looks like. And I showed you that brief video earlier as well. You can see that it looks quite messy. The neurons occupy 3D space. And as I mentioned and I'm emphasising, they really connect with each other with a high degree. So it's a complex network, it's a highly connected network, and this is what we're trying to emulate in building a synthetic brain. An important aspect of that complexity in the structure of the real human brain is that it enables something called synaptic plasticity. What this means is that it allows the brain to continuously respond to input data and information and continuously reconfigure all the synaptic connections that it makes with all the neurons. This is happening all the time in our brains. And this synaptic plasticity is what neuroscientists now attribute to our capacity to remember things and to learn. In other words, our intelligence. So synaptic plasticity is the key to actually emulating general intelligence as we have it in our brains. And the way to do this is by emulating the complex network structure of the human brain. That complexity is absolutely essential. So, are there any technologies that where we can actually start to emulate that complex network structure that we see in the human brain? Well, of course, the answer is yes, because otherwise I wouldn't be here this evening. So this is the best technology that we have at the moment today of something that is really now starting to resemble the structure and also the function of the human brain. This is what I've called here a neuromorphic nanotechnology. So let me describe what it is that you're looking at here. First of all, it's an image taken with an electron microscope. An electron microscope has incredibly high resolution, and therefore it's used quite often to image nanotechnology devices, which is what this is an example of. What you're looking at, all those individual strings that appear to have this very messy structure, they are actually nanowires. So nanoscale wires. In this case, they're made out of primarily silver. But they're about maybe 100 nanometers in width and much, much longer in length, typically microns in length. These nanowires actually have incredibly interesting properties. And these interesting properties only emerge because they have this nanoscale structure. Now, what's of interest to us for the neuromorphic application, the brain-like application, first of all is the structure. And you can see immediately how much more similar this type of structure is to a real neural network compared to other structures that are based on semiconductor device technologies. But secondly, in addition to the network structure that these nanowires can produce, it turns out that because they form this complex network, they actually overlap in many, many areas. And the locations at which the nanowires overlap with each other, when you put an electrical stimulation over the network, they actually behave in exactly the same way as synapses do, in the sense that where two wires overlap, they form a junction. There's a gap between them. And when that junction experiences an electrical stimulation, it actually drives ions from one wire to the other in exactly the same way that neurotransmitters are transmitted across synaptic connections between neurons. This is incredibly exciting. And the results that we have to date actually show that you can put different types of electrical stimulations across these networks and get the network to exhibit memory behaviour. You can also train the network by applying the same stimulation over and over again and getting the network to replicate that signal. So I'm going to show an example of how we can get this kind of nanotechnology that emulates the brain to actually start getting it to learn something. So what I'm going to show you now is a movie. And you can see on the left-hand side the number 2 that's being flashed up there. Each one of those little squares on both sides represents an area where we have this neuromorphic nanotechnology, synapses if you like. And electrical stimulations are being delivered to mimic the shape of the digit 2 and also the digit number 1. The difference is that the digit number 1 is being delivered by electrical stimuli at a much, much faster rate than the electrical stimuli that are used to generate the number 2. At the end of this, you can see that the number 1 is retained much more strongly. There's sort of a faint resemblance of the number 2 behind it, but it's the number 1 that has this very strong retention by this device. And that demonstrates to us that we can actually control the way that this device remembers things by simply controlling the rate at which we're delivering information. So we can control the repetition rate and therefore control how it remembers things. This is crucially important because this is exactly the way that we remember things. When we want to remember something important, whether it's for an exam or something else that we're interested in, we read or go over something over and over and over again, and we get memory from that. And importantly also, the human brain exhibits two different types of memory, short-term memory and long-term memory. And we can actually start now to see those differences in the formation of these two types of memories from this type of nanotechnology neuromorphic device. It's actually incredibly exciting. Now, short-term memory and long-term memory, the neuroscientists have pinned that down to being attributable to synaptic plasticity. So again, it's this complex network structure that this device is able to produce that allows it to display these different behaviours of memory that are now starting to emulate the way that the real human brain works. So where are we going with this? So let me just finish up with some views of my own. So in 2006, the World Economic Forum put forth their view that the 21st century is now witnessing what they've called the fourth industrial revolution. And of course, we saw the first industrial revolution in the 18th century. 19th century, we saw another revolution from the introduction of electricity, and then of course 20th century is perhaps best well known by the invention of the transistor and hence the subsequent electronics and computer industry. Well, the fourth industrial revolution is characterised by several emerging breakthrough technologies, which include AI, of course, the Internet of Things, nanotechnology, and space technology. Now, the fourth industrial revolution is going to be characterised not by just one of these things. It's going to be characterised by the convergence of all of these and probably more breakthrough technologies that we are yet to see. We're only at the beginning of the 21st century. Where does synthetic intelligence fit into this? So, I've explained to you how synthetic intelligence provides an alternate approach to AI, software-based approaches. I've also shown you how important nanotechnology is to synthetic intelligence. We really couldn't have realised a synthetic intelligence device without nanotechnology. The Internet of Things basically describes how the world is becoming increasingly connected on the global scale. And at the moment, that's being driven by AI and the requirements of AI. But that's actually unsustainable because of the power requirements of AI. You think about how many times a day you do a Google search and then stop and think about how much power that actually consumes. A typical Google search consumes about, I think it's about 1 kilojoule of power that corresponds to turning on a light bulb for about 15 seconds. And you think about how much of that goes on every day. Most of that power is required to keep the servers going, so to keep them cool and to store the data. That cannot keep going on if we really are going to be experiencing this industrial revolution. We need better ways to be interconnected and cleverer ways. Space technology I haven't touched on yet, but in my view, space technology is the killer app for synthetic intelligence for the following reason. We are now seeing a real push, like a genuine real push backed by money for colonisation of the moon and also Mars. And if we're going to do this, we actually need synthetic intelligence devices, autonomous systems with synthetic brains in them, to send them out and actually prepare the moon and of course Mars for human colonisation. For Mars, it's absolutely critical. There is no way we can actually send manned space missions out to Mars first off. We need to be able to send machines out there, and those machines need to be able to think adaptively with minimal human interventions. There are going to be long periods of time where we are not going to be able to communicate with those kind of devices. So they really need to be as autonomous as possible. And in fact, NASA is now preparing autonomous systems with increasing levels of autonomy for their next Mars rover mission for 2020. So this is where I see the real application for synthetic intelligence, or at least the most exciting one in my mind. But just to finish up my presentation, I want to leave you with a quote from the famous British mathematician, computer scientist and logician, Alan Turing. Thank you very much for listening.